Hi, welcome to this course on quantum mechanics. The first set of lectures will be on the formulation of quantum mechanics. So we'll be discussing the mathematical formalism of quantum mechanics. So the particular mathematical formalism that we will discuss is called as the Hilbert space formalism. The first class is introductory in nature. The aim is to provide an overview of the theory. So the mathematics of quantum mechanics, the logic of quantum mechanics is different from that of classical mechanics. And I want you to have an idea of what are the kinds of things we are going to do during this course. The references are these. The main reference, the one on which your syllabus is based on, is Modern Quantum Mechanics by J.J. Sakurai. And I have included two more references. One is Quantum Mechanics, the Theoretical Minimum by Leonard Susskind and Art Friedman. The third one is the Principles of Quantum Mechanics by Paul Dirac himself. So Dirac was one of the founding fathers of quantum mechanics. And this will be the main reference for throughout the course, and we'll be trying to solve problems from this particular textbook, and we'll be following derivations and detailed calculations from this particular textbook. The second one is actually, it has a lot of interesting insights, and it's not exactly at a high, it's not exactly a high level textbook. It's more like an introductory textbook, but it includes a lot of mathematical insight. The third one is representative of another kind of textbook. Okay, it has Dirac's characteristic style. It's brief, it's concise, and it's beautiful. It's a classic. Right? So I've just included these three textbooks as representatives of different kinds of textbooks. Actually, of course, there are other very good textbooks out there available with a lot of problems. So if you want to solve many problems for competitive exams, etc., there's a textbook by Zetterli, and there are textbooks by Griffiths, Shankar. Okay, so and if you are really interested in the theoretical details, there's this textbook by V.K. Thangappan. Okay, so there are so many textbooks that we can follow, but when we study it for the first time, I think it's better to follow one particular textbook for following the calculations, etc. So just take this textbook and try to understand everything in it. Okay, that's what we'll do during the course. Okay, so we'll follow the textbook by J.J. Sakurai, and we'll try to understand everything that's given in there. So before we dive into quantum mechanics, as I said, this is an introductory lecture. We'll just discuss the vocabulary, some of the words which we have been using all the time and which we will be using over and over again. We'll just have a quick look at classical mechanics, which you have already studied. And I'll try to tell you how quantum mechanics is different from classical mechanics. So quantum mechanics is not a particular theory within the framework of classical mechanics. It's a different set of, it belongs to a different kind of logic. So we'll just try to appreciate the difference between these two. And also quantum mechanics arose out of a lot of experiments. Okay, so it came out of the need to explain a lot of experimental data. There's a very good thought experiment that is representative of all these experiments. This is the double-slit experiment. So the double-slit experiment is a thought experiment that we will discuss. This can be done. This has been done. This is an experiment that has been actually done, but we'll talk about it as an ideal thought experiment. And then based on this experiment, we'll try to understand the basic principles of quantum mechanics, the basic principles that goes into the mathematical formalism. Okay, or we'll try to understand what's the kind of world that we are trying to describe. Okay, that's the main purpose of discussing the experiment, the thought experiment. We'll try to understand what's the kind of world that we are trying to describe using quantum mechanics. We start with the vocabulary. We'll be using the word system. By system, we simply mean a collection of objects, particles, fields, waves, or whatever. Okay, whatever thing that you are studying about, it's called a system. And then there's this term that we'll be using, dynamical system. Dynamical system means a system that changes with time. That's all. And then when there are dynamical systems, we try to find out the dynamical law. Dynamical law is a rule that tells us the next state given the current state. Okay, so dynamical law is actually, if you want to study a dynamical system, a system that changes with time, All right, we'll try to find the equation that governs the evolution of the system in time. All right, so for example, Newton's second law, it governs the evolution of a classical system, a classical particle in time. Okay, so this is an example for a dynamical law. And then we already used the word state here. So the basic idea is that in physics, most of the time we are preoccupied with trying to find the future, to predict the future. Not only the future, we are trying to understand how systems change in time. Okay, so that's why we have a dynamical law, and we already used the word state here. What do we mean by a state? Okay. By state, this is what we mean: everything you need to know with perfect accuracy to predict the future, given the dynamical law. All right. So if Newton's equation, if Newton's second law is the dynamical law, if Newton's second law is the equation that governs the time evolution of a given system, then what do you need to know about the present? What do you know? What you need to know about the present so that you can predict the future. Okay. This collection of information is what we refer to as state. Okay. And then once we have state, we can talk about the state space. All right. So in physics and in mathematics, space is usually used in two different senses. Okay. Sometimes we talk about the physical space, as in space-time. All right. And other times we talk about it as a mathematical set. So here, by state space, we mean it's the collection of all the states occupied by the system. It's a collection of all the states occupied by the system. All right. So what is it? It's a mathematical set whose elements label the possible states of the system. So it's just a mathematical set. Each element in the set is a possible state of the system. All right. So this we call it as state space or space of states. So with that, let's have a quick look into classical physics. You have already studied classical mechanics. So what is classical mechanics actually? So classical physics is a set of principles and rules. Okay, it's an underlying logic that governs all non-quantum phenomena. Okay, so basically by non-quantum, I can roughly translate it as macroscopic, right? So classical mechanics roughly deals with the macroscopic world, where quantum mechanical quantum mechanical phenomena, quantum mechanical uncertainty is not important. Okay, so classical physics or classical mechanics in itself, it's not a theory. It's not a theory, but it's a framework. It's a logic. It's an underlying logic. What do you say? It's a framework within which you can construct theories. Okay, so it's a framework. It's a logical framework. It's an underlying logic within which theories can be constructed. All right. So for example, within the framework of classical mechanics, if you look at a physical system, we describe it by positions and momenta. If it's a particle, we talk about the state in terms of the positions and momenta. Or we can have some generalizations of these concepts. All right. So we'll either talk about position and momenta or appropriate generalizations. All right. So this is the basic logic of classical mechanics. And once we talk about positions and momenta or their generalizations, we try to understand how these things change, how these variables change with time. All right? So there will be an equation of motion that governs the change, that governs the time evolution. For example, you could talk about Newton's second law, or equivalently Hamilton's equations or Lagrange's equations, or more generally the principle of least action. All these are equivalent, and some of them are easier to use in certain different situations, but all these belong to the same framework called classical mechanics. Now, there are many theories under the broad umbrella framework of classical mechanics. For example, Newton's law of gravitation. All right, so if you look at Newton's second law, F equal to ma, right, F equal to ma, it is actually agnostic about what the forces are. All right, it doesn't talk about what kind of forces exist in nature. Right, for that we have got specific theories. For example, Newton's law of gravitation. Right, it's a theory within the framework of classical mechanics. The Maxwell-Faraday theory of electromagnetic fields or electrodynamics. It's another example for a classical theory, right? Or even the general theory of relativity. It's another theory that describes gravity, right? That describes gravity in terms of the geometry of space-time, etc. It's also a classical theory. Now, as an example for a dynamical law, let's look at Newton's equations. The dynamical law is F vector is equal to dp by dt. So you can solve this equation and it will tell us how how the state evolves in time. So given that this is the dynamical law, right, you can talk about it in one dimension, or this is in three dimensions. For simplicity, let's talk about it in one dimension. So you can write F equal to dp by dt. All right. And what is P? P is equal to m dx by dt, or P is equal to mv. All right, if you are talking from within the framework of, if you are talking about Newton's second law, then P is equal to mv, F equal to dp by dt. So this equation, this is a differential equation. You can integrate this once, that will give you the momentum as a function of time. You can integrate it once more, it will give you the position as a function of time. All right. So in order to integrate this twice, you need two constants of integration. You need two constants of integration, or you can say that these are the two initial conditions. So you need two initial conditions. You need two initial conditions to start working, or to start working with Newton's second law. All right. So what's the information that you need about the system at this particular point of time so that you can solve this equation? You need the initial conditions, you need the position and momentum. All right. So this is the reason why we say that the state is specified by the position and momentum. If you give the position and momentum of a physical system, then you have specified the state of the system. All right. So by solving this equation for a given force, you can actually find x of t and p of t, how position and momentum change with time, or how the state changes with time. Okay. So this is how we define the state of a physical system in classical mechanics. And the state of, so we also talked about this space of states. We talked about space of states, or state space. In this case, so what was state space? It was a set of all possible states of the system. So in this case, in order to specify each state, you need to give each possible state, you need to provide the position and momentum. All right. So the state space given the above dynamical law is called the phase space. You might already be familiar with this word, phase space. So phase space is a state space of a classical mechanical system. It's a space of states. All right, it's a set of all possible states of a classical mechanical system if Newton's second law is the dynamical law. All right, so this is true also for Hamilton. If you talk about Hamilton's equations of motion, again, the state space is called the phase space. All right, so for any classical system in this sense, we can talk about the state space as a phase space. Okay. So what in this space, each point in phase space, so each element in this set is a possible state of a system, okay, of the system. Each point in phase space is a possible state of the system. So you can think of it as some 6n-dimensional space. Each point, in order to specify each point, you need 6n numbers, 3n positions and 3n momenta. All right, where n is the number of particles. Okay, and that would give you one possible state of the physical system. So corresponding to any physical system, you can think of a phase space. Okay. All right. So that was an overview of classical mechanics. So I hope you were familiar with all these things. We just refreshed a little bit. Now let's go into quantum mechanics. Okay. Now what is quantum mechanics? Quantum mechanics is also a logical framework. It's also an underlying logic, but it's different from classical mechanics. So quantum mechanics is a framework, a set of rules, an underlying logic within which different specific theories can be constructed. So quantum mechanics is actually a different logical framework from classical mechanics. Quantum mechanics arose out of observations. This is very important. The quantum mechanics, the laws of quantum mechanics were forced upon us by observations, by the way nature actually behaves. Okay, so quantum mechanics arose out of observations which showed subtle discrepancies between the actual behavior of the world and descriptions of classical physics. What does this mean? It means that once we have accumulated a lot of experimental data, we see that we are not able to describe these observations using any classical theory. All right, classical mechanics completely fails in this case. All right, so the observations related to atomic and subatomic realm. All right, so the what do you say? The observations of atomic and subatomic world, or the behavior of atomic subatomic world, it cannot be described using the classical logic. It cannot be, you cannot construct a theory. Okay, we saw that it's not possible to construct, or it was clear that it's not possible to construct theories of subatomic phenomena from within the framework of classical mechanics. Okay? So in short, classical mechanics is a failure when it comes to the microscopic world. Classical mechanics is a failure when it comes to microscopic world. Okay. Now, the study of atomic phenomena confused people because people thought at that time that classical physics is indeed the correct framework within which we can study the universe. Okay, so people thought that, all right, classical physics is complete, the logical framework is complete, we just need to tie some loose ends. That's what people thought at the time, right? But the study of atomic phenomena was completely confusing to physicists, and people were trying to make sense of these things, trying to construct theories which describe atomic phenomena. And it led to two successful theories, matrix mechanics and wave mechanics. Matrix mechanics mainly by Heisenberg, Werner Heisenberg, and wave mechanics by Erwin Schrödinger. So in the beginning, these two theories looked entirely different, but Dirac uh, actually showed that, okay, he actually showed that these two theories are not separate theories, but these are two different representations of the same underlying theory. Okay, so it's Dirac's formulation that we will be discussing in this course, and we'll see how matrix mechanics and wave mechanics are actually different representations of the same underlying theory. All right, so we'll be studying Dirac's formulation. Now, all right, quantum mechanics is a logical framework, I said. Okay, now how is quantum mechanics different? All right, so throughout the course, we'll try to appreciate how quantum mechanics is different from classical mechanics. But let me just summarize the points where quantum mechanics is actually different. Okay, so quantum mechanics deals with the behavior of objects which are so small that we humans are ill-equipped to visualize them at all. Okay, so this means that quantum mechanics studies the world. Okay, quantum mechanics studies a world which is completely out of our experience. Okay, so it's we cannot visualize them at all. All right, so these, for example, these electrons, these are so small that it's not possible to have any visualization at all. Our visualizations are according to the classical logic, but when things get really small, these visualizations do not work. Individual atoms are near the upper end of the scale in terms of size. Okay, so we said that we are dealing with small objects. Okay, small objects. The question is how small. So you can say roughly the size of an atom. So if things are smaller than the size of the atom, then it's surely quantum mechanics. And we'll talk about electrons as the representatives of the subatomic world, right, or the microscopic world. So electrons will be considered throughout the course. Electrons will be considered as the representatives of the microscopic world, of the microscopic world. Okay. Now our sensory organs, okay, it has to do with evolution probably. Our sensory organs are simply not built to perceive the motion of an electron. All right, so we cannot perceive the motion of an electron using our sensory organs. All right, so we don't have that capability. The best we can do is to try to understand electrons and their motion as mathematical abstractions. Okay, so we'll try to make things. Actually, this is what actually Heisenberg tried to do. He tried to make an abstract mathematical formalism so that it does not lead to any visualization. Because if you try to visualize an electron, you will probably go wrong. All right, so the best way to think about an electron is as a mathematical abstraction, which obeys certain kind of logic, certain rules, but different from what we are familiar with. Right? But then you can ask this question. Classical mechanics is also filled with mathematical abstractions, right? So even in classical mechanics, we talk about ideal system. We talk about point masses. Point masses means objects which are confined or point particles, right, which are confined to a point which has no dimensions. Okay, this is a mathematical idealization, but we talk about it all the time. We talk about rigid bodies, perfect rigid bodies, whereas in nature there are no perfect rigid bodies. Okay? We talk about inertial reference frames which extend throughout the universe, whereas in actuality there are no such inertial frames which can be extended throughout the entire space-time. Okay. We talk about positions, momenta, fields, waves. Okay, we cannot really imagine this electromagnetic field. We know how to describe it mathematically, but it's difficult to imagine the electromagnetic field, for example. We talk about waves. Okay. Now the question is, why is quantum mechanics any different? All right, I said that it's abstract, but then we use abstractions in classical mechanics also. Right, but quantum mechanics is different mainly in two ways. The first is that it's a different kind of abstractions. In quantum mechanics, we use different kinds of abstractions, which we will see during the course. I just want you to appreciate this difference. Okay. So the quantum abstractions are fundamentally different from classical ones. For example, we'll see that the idea of a state in quantum mechanics is conceptually very different from its classical counterpart. For example, I said that for a classical system in one dimension, you can talk about the state like this: x comma p. You specify x comma p, then the state is specified. The physical state of the system is specified. Okay. But in quantum mechanics, we'll see that you cannot specify the state like this. All right, we specify the quantum mechanical state in entirely a different way. All right, you might have already studied about wave functions, so you might have already seen that states are represented by wave functions, etc. But we'll come to that. Okay. All right. And states are represented by different mathematical objects, not position and momenta, but some things that we call as wave functions. Okay, these are different these are entirely different from anything like a position and momentum or their generalization. Okay, so you cannot get a wave function by generalizing a position and momentum. All right. And the states are represented by different mathematical objects and have a completely different logical structure. Okay. And you'll see that there will be a lot of complex numbers, and in classical mechanics we use complex numbers only to make our calculations easier. Okay, and in the end we'll take only the real part, but in quantum mechanics we'll see that complex numbers are fundamentally important. So in every way these quantum mechanical abstractions are entirely different from the classical mechanical abstractions. And there's another fundamental problem, which is the relation between state and measurement. Right? In classical mechanics, if you specify the state of the system, you give the position and momentum, you can find, okay, we can calculate all the measurable quantities associated with the system. Okay, if I say that it is at a position x and it has a momentum p, you can find anything. You can find its kinetic energy, you can find its angular momentum, everything. All right. So specification of the state in classical mechanics is also the specification of measurement outcomes. All right. So if I specify the state, that automatically specifies the possible measurement outcomes. If I know the state, I can calculate all possible measurement outcomes. I'll know with certainty what are the possible measurement outcomes. So if this is the state of a classical mechanical system, I can ask what's the angular momentum, and then you just take r vector cross p vector. I can ask what's the kinetic energy, just find p square by 2m. All right, all these things, anything. So in the classical world, the relationship between the state of a system and the result of a measurement on that system, it's very straightforward. It's actually trivial. The reason is that the labels that describe the state, like position and momentum, okay, are the same labels that characterize measurements on the state. Okay. In quantum mechanics, states and measurements are two different things. Right? In classical mechanics, there's no need to talk about states and measurements separately. There's no need to talk about states and measurements separately. It means the same thing. But once we go into quantum mechanics, we'll see that states and measurements are entirely two different kinds of things. And the relationship between the state and the possible measurements, it's very subtle, it's it's not complicated, but it's very subtle and it's completely non-intuitive. It's very difficult to understand this completely. All right. So in quantum mechanics, we have a mathematical framework which works perfectly, but there are certain things, underlying things, which we don't yet understand completely. Okay. So I think it was Feynman who said that no one completely understands quantum mechanics or something like that. He said something like, no one understands quantum mechanics. This is true. Okay, it's true in one sense. We know we understand quantum mechanics in one sense. It means that we know how to make calculations. We know how to make predictions regarding physical systems. But what we don't understand completely is, what does all this mathematics mean? All right, why does it work and what does it mean? This part we don't completely understand even today. Okay. But throughout the course, of course, we'll be dealing only with the part that we understand, how to make calculations, how to predict probabilities, how to make predictions, etc. This is the only part that we'll be dealing with during the course, and maybe here and there we'll talk about the part that we don't understand completely, just for a pastime. All right. Okay. Now, we said that the mathematical framework of quantum mechanics arose out of the necessity to describe experimental observations. Okay. So, there were so many experimental observations which were completely surprising uh, if you look at it from a classical viewpoint. Okay, so there were surprising observations. Let's say that there were surprising observations. Why do we say surprising? Because they don't follow, these observations do not follow the classical logic. All right. Now, all of the surprising experimental observations can be summarized by a thought experiment, the double-slit experiment. So we don't have to talk about all these experiments. We'll just talk about one. Actually, we'll talk about two experiments. First, we'll talk about the double-slit experiment. Okay, and it summarizes basically all the weird things that happens in the microscopic world. So this is an experiment, a thought experiment that was popularized by Richard Feynman. So we'll start with this. Okay. And you'll see that Dirac's book also makes a mention of the double slit experiment. So I think this is a good point to start. All right. Now, on observing this behavior, we shall try to construct a theory. All right. Actually, we won't try. We'll just pretend. We'll pretend to construct a theory that can describe nature at this level. Okay. So this is how physics works. We look at the world. Uh, we look at nature using our experimental apparatus. Then we collect data. Now we try to describe this data. Okay, so we'll try to pretend, or we'll pretend to construct a theory that can describe the nature at this level. So by looking at the double slit experiment, we'll try to understand how the nature behaves, microscopic, or how the microscopic world behaves. So from the experiment, so here I'm just describing the experiment. Okay, here I'll be just describing the experiment. From the experiment, we'll just understand how the microscopic world behaves, behavior of microscopic world. Now, once we see how the microscopic world behaves, we'll try to describe it using a mathematical theory. All right. And also there's, again, as I said, there's this interpretational problem in quantum mechanics, how to interpret the basic mathematical, uh, how to interpret the mathematics of quantum mechanics. This is an open problem still. It's not a completely solved issue, not yet. All right. So throughout the course, I will have a specific interpretation in my mind. All right. So I maybe will make it clear later on. Okay. So the language that I use, that I'm going to use, will be based on a specific interpretation of the mathematics. All right, which I will talk about later on.